Hello, everyone, and thank you very much for inviting me to give the first talk in Easter term in the Lennard-Jones Centre. So I will talk to you about atomic cluster expansion, which I called here a framework, and I hope to convince you that it is really a framework, and it also provides a recipe, and then whatever you can make from it. And I'll show a few examples what I am making from it, and hopefully you yourself can go and try out this machinery to do what you are interested in. So the outline of the talk is first, I will just quickly talk about representing atomic environments, which is something that most kind of computational theoretical person nowadays have come across with. Then I will describe the atomic cluster expansion as this framework. I'll talk about invariants and equivariants. You will see what I mean by that. And in the end, I will just kind of flag up what our future or current work direction is. So what is an atomic structure? Atomic structure is something like a molecule, as you can see up there. It has atoms, so particles, and those particles are atoms in our case. And these particles have positions, and they also have something that I call attributes, which are properties of these atoms, like their chemical elements or charges. And then, so we want to do some machine learning, in our case, with these structures. So we have to plug them into a computer, and the most usual way of doing that is to specify them in these kind of a format where we have the element, so that is an attribute, and then we have the position x, y, z coordinates in Cartesian. And then we want to map these input into something like the potential energy, but it can be something else as well. And so you can see that this is really a non-trivial task, because there are very different symmetry requirements of the potential energy and this kind of input as we have it here. So our machine learning model would really struggle to pick those up. So here comes in symmetry to the play. And so just here on the right, you can just see just a little notation. When you see a sigma, sigma means basically a configuration or the state of an atom. So its position and its like chemical element, and it also might have some learnable numbers attached to them later. So the usual target properties of the machine learning are something like a potential energy, or it can be something else like a binding affinity if you want to go more AI, or it can be density of states, dipole moment. And these are all things that have some kind of a symmetry with respect to the input of the model. And so this I can express in this very general way. So what this means is that if I apply a transformation Q to the input, so this can be for example, general rotation, then my model's output of the transformed input has to be the same as the model's output of the original input transformed. Okay, so if you have invariant or equivariant properties, then that can be expressed this way, and we want our model to obey this. And it's always the case that if you have a molecular or an atomistic structure, and you have one of the properties that I've given examples there, they will all obey different a relationship like this. So, for example, something like a dipole moment will rotate with the structure. So as we rotate input, it will rotate with it. And this is something that we really have to bake into our models, because we know them in advance, so we don't want the models to have to learn it from data. We want it to be obeyed by design. So how do we go about building symmetric representations? That's what my talk will be really about. We start with an input structure in a non-symmetric way. Then we transform it into a symmetric form. So that will be kind of a set of numbers that now obey the symmetries. So basically, if you rotate them, they either rotate with the structure, of, for example, if it's an invariant, then they do not change. And then we can kind of do a downstream task of fitting a model, and that can be a linear model, or it can be a neural network, or a kernel model, and then we get some kind of a target property out. So just quickly the symmetries, because most people probably know it. The most important symmetries that we care about are going to be translation, then it's going to be rotation of the input structure, and also the permutation of the like atoms. So that is basically just an indexing. So if I swap two oxygen molecules, I still specify the same structure. So now I want to talk about atomic cluster expansion. And so what it is, it's just notation as a reminder up there. So atomic cluster expansion is basically a very systematic framework or a recipe to build these polynomial features of atomic environments. And this was published in 2019 by Ralph Draughts. And then sort of our group started using it and building from it ever since. And I believe there has not been a talk about it in the Lennard-Jones Centre in the past well, since we started. So it's probably, so I went really back to the basics, and I will present my view on this Droughts paper, and then we will go from there. So the most crucial ingredient is something that is called the one particle basis. So if I have an atom, then this one particle basis will be a function of one of my neighbors. That's why it's called the one particle basis. And it has two parts. It has a radial part, which is this R and L, which acts on the distance, and it has a YLM, which is a spherical harmonic, like the atomic orbitals, and this will describe the angular dependence. So where is my neighbor in angular space compared to me? So, and then we evaluate this one particle basis on every one of my neighbors, and then I sum over my neighbors. Okay, so what I get is basically a set of the values for these functions, and it's going to be now permutation invariant with respect to my neighbors because I'm summing over them. So if I swap two labels, then that doesn't change the value of this kind of feature. So that this is this A function. So when you see an A is this permutation invariant description of a local atomic environment. Now what we will do is we will go to something called the body order expansion. And this is a usual technique in approximation theory and also in the physical sciences. And so we will try to approximate. So here I'm giving the example of the energy, but it can be applied to any property. We'll approximate something, so here the energy, in this hierarchical form. So what I mean is that we will have terms that depend on a single particle, and then two body parts, which will depend on two particles at a time, three body parts, which will depend on three at a time. And this is an expansion that converges. So if you have an n particle system, then if you expand it to n order, then you will always be able to converge. But the hope is that by learning low dimensional structures, we will be able to truncate it much quicker than n, and then we'll get some transferable body ordered representation of our target property, for example, the energy. So what do we do with these A functions that we have created before? So those A functions were two-body, right? They were depending, their value depended on an atom and one of its neighbors. So what we can do is we can say that, okay, we have a constant term, that's one body, that's not too interesting. Then we can have the two body, which we can parameterize using these A functions because they were complete. We had a complete set of radial functions. The spherical harmonics span the space of functions on the sphere. So this is going to be able to represent any two body function. And what we can do is we can take products of this. So if I take a product of two of these A functions, then they will be three body because they will depend on the center atom and one neighbor, and center atom and another neighbor. So that's three body functions. And these will be very general three-body functions. So they will be three-body functions of Rij, Rik, so two distances, and also via the spherical harmonics, they will depend on theta ijk, so the angle between them. So we can then, in principle, represent any three-body function. And then if we go further, we multiply more of these A functions together, then we can represent any function in this hierarchical form. And this A which is the product of these permutation invariant functions, is what I call here the product basis. Okay, so moving on, the one thing that we haven't talked about yet, so we have permutation invariance and we have a complete description, but we do not yet have the rotational symmetry built into our structure. And sort of a good hint how we can achieve rotational symmetry is that we have put all of our rotational dependence into these spherical harmonics. Okay, so the radial basis was just distances, and then everything that depends on angular or that changes with rotations of the system was put into the spherical harmonics. And then we have this very nasty thing here. So what is this? So we have the product basis, so or description, which is complete and permutation invariant, and then we apply it to a rotated input. And then we kind of integrate over all rotations. So that means that we basically, the inverts, this is an average over all possible rotations. And if you think about it, so this will create invariance. So if I average over all possible rotations, then whatever is left cannot depend on rotations. Okay, and so conveniently, we have written all of the rotational parts. The rotation only acts on the spherical harmonics. And we have sort of very well-established 20th century or physics about angular momentum and how to sum spherical harmonics. So basically, this integral that was so nasty ends up being just a simple linear combination of these product basis functions with the Clebsch-Gordon coefficients, or for the higher order base functions, like a general version of them. So we can then write, for example, in linear A's. So that's what I will talk about in the next part of the talk. In the linear atomic cluster expansion, we can express, for example, the potential energy, just a linear combination of these B basis functions. And this is very nice for a few reasons. So one of them is that this is a complete representation. So you can really converge this. And this is also sort of body ordered, so you would hope that this body ordering will help you with generalization. So I will just very briefly show some results. So here is, for example, MD17 is a data set of small organic molecules, and the task is to fit a force field on 1,000 configurations. And so many people have done it, and that's why we do it as well. And so here are a few kernel models, some feed-forward neural networks, some classical force fields, and here there are two message-passing neural networks, which basically is a mechanism to learn a symmetric representation rather than have one sort of fixed expansion. And I mean, there isn't, all you have to take home here is that the blue ones are basically best in this task. And you can see that we can really build linear models with linear regression that match the accuracy of these other kind of high dimensional or nonlinear regression methods. And that was the case when we published this paper. And then surprisingly or not, there was another model coming up in the literature, which actually, so this was very recent, like half a year ago, or even more recent than that, which now kind of has another factor of 2 to 3 in accuracy. And what they did was a message passing scheme, but they just did it much better than anybody before. So they kind of, rather than having a fixed expansion of the neighborhood, they kind of iteratively expand the neighborhood. And they used some equivariant features, and I'll show how the whole ACE actually can accommodate that. And so this atomic cluster expansion, if you generalize it, this NACWIP model will be part of it, and I'll show that at the very last slide of the talk, because that's the future work part. Okay, so just to show a bit more about what we can achieve with these force fields, we have come up with one of our own tasks, and this is something that people actually start to use more and more, this data set, where we can fit a model on 300 Kelvin configurations, thermal configurations of this 3 BPa molecule. And it's interesting because it's a very floppy molecule, very flexible. And you can see that in this alpha, beta, gamma kind of dihedral space, there's only a few pockets sampled. And then there are test sets which are at higher temperatures. And then we can measure how well the models extrapolate. And we can also plot the dihedral energy surface of this molecule. So for example, we can fix the middle angle and we can rotate these two. And you can see that the linear atomic cluster expansion is actually reproducing very faithfully, and some other models, high dimensional regression models, are kind of fuzzy or get some features vastly wrong, whereas the classical force field is nice and smooth, but it's just really inaccurate. So classical force field is the is what people use before machine learning to do this. Okay, and so just one last thing that you know, it's not everything to be accurate. You also have to be fast to be useful. And so this atomic cluster expansion is providing a framework where you can converge your features systematically. So that means that as I'm adding more and more features, more and more basis functions, I get lower and lower errors, but then my model gets slower and slower. But as you can see, in comparison to the other models, it is a super efficient implementation. Okay, so that's all nice. So it seems like we can do very good models of local environments. So what is next? And one of them is to go beyond these local models. And so what we do is we can write the total energy as a sum of a short range term and a long range term. And so far in these small molecules, we kind of conveniently forgot about the long range term. And apparently we could do that, and the models were still really accurate. But sometimes we actually have to deal with it and for some systems. So the short range we can still fit directly. And then the long range, for the long range, we have the physics. So the physics of long range interactions is dispersion or electrostatics. Usually these are the dominant parts. And these have very kind of well-established physical functional forms, but they have parameters in them. So what we can do is we can fit these parameters as local functions, and then we can plug them into the physical models, and then we can kind of recover the long-range physics as well using our machinery. So here just, you know, it's another one of those ugly equations. I'm again kind of rotating my input, and then I plugged it into these product basis, and then I average over rotations. But here I'm not quite averaging out all rotational degrees of freedom, but I'm actually looking at these components of the of a Cartesian vector. So it's like, for example, like A alpha can be an X or a Y or a Z, and I can evaluate this integral. And all I get with this is a different set of CG coefficients, which will now recover properties that transform, like, for example, the X unit vector or the y unit vector or the z unit vector. And this is going to be necessary because we want to fit, for example, dipole moments. So the model that I will show here is the following. We want to model water, and in water, especially if you want to study interface properties, long-range interactions cannot be neglected, as we know from Steve, I think, partly. And so we create a water model where we have fixed charges on the atoms, but that would be vastly wrong for the long-range interactions. So we actually fit a dipole component on each atom, and then we will plug that into a long-range part. So we'll have a long-range model that has charge-charge dipole and dipole-dipole interactions, and then we will have a short-range correction to that. Okay, so but for that we need to be able to fit the dipole moments of the atoms. So we did that, and we wanted to go all out. So people have done, you know, neutral molecule dipoles before. People have done protonated water cluster dipoles. We wanted to do everything. So can we do negative, neutral, and positive water clusters, all of them together in a single model? And the answer is that actually we can, and we can surprisingly well in a super data efficient way. So what we get is really these are percentage errors. So the negative and positive water clusters have a percentage dipole error below 0.5%. So and the neutral clusters have a larger percentage error, but they have a much smaller dipole. So in absolute dipole error terms, these are all kind of micro dBi errors. And it's also interesting to note that we only trained the model on up to 6 water clusters, and we evaluated it on larger ones as well. And we can see that the errors kind of deteriorate a bit, but not too much. So the hope is that we can actually then fit this to coupled cluster accurate data, and then we can have a coupled cluster accurate reactive water model, because everything is reactive in this short range, like A-slide models. We haven't specified what is connected to what. So we can really create a coupled cluster accurate reactive water with short range and long range together. And so we are working on it, and we are working on validating it, but I can already show like a movie where there is a proton wandering around in a water cluster, and it's work in progress to actually verify this a lot better and do some systematic studies. But this is one of the kind of future directions of ours that we are currently working on. So with that, I just want to say 2 more slides about how to go beyond this fixed transformation. Because what we have seen so far is we have an input structure, and this atomic cluster expansion was this very systematic recipe that allows us to go into a symmetric representation. But we have seen that there was that one necrit there, which did it in a not fixed way, but in a learnable way, and they were very accurate. So can we make the atomic cluster expansion learnable in some way? And the answer is we can. But so let's see what is the A's that are presented. So the atomic cluster expansion that are presented starts with the state of an atom, and it kind of expands its neighborhood in this B basis, and then applies a linear transformation to get a readout. But the readout can be energy, dipole, or whatever you are interested in. So what we can do different in something that we call multi-A's is that we can actually have a set of these B basis functions, not one but many, and each of them can learn to attend to different chemical elements, and they can all have different radial basis functions, for example. So we can put a lot of parameters into this model, and then we have to apply a nonlinear optimization. And then we kind of mix these. So then we apply a linear, and then we do an update. In this update phase, we mix them all together, these different basis functions that we had. And then we get kind of we get some features on each atom. And what we can do is that we can expand not only the positions of the atoms around us, but we can expand their state as well. So what happens if we just stack 2 of these aces on top of each other? And that is something that, so Ilias is sitting up there. He's really leading the work of going beyond the single layer ace, but some preliminary results show that we can actually recover neck-whip accuracy with just 2 layers of this ace, and we can be about 10, 20 times faster. So that's probably one of the future directions, is really to go to these modern GPUs and just have a bit of nonlinearity, but still keep these systematic ace ideas. And yeah, I think hopefully Ilias, when he's invited, will give a full talk on how to actually do this. Okay, so with that, I'd like to conclude. So I hope to have shown you that you can use this atomic cluster expansion as a very systematic framework to create efficient symmetric polynomial representations of atomic environments. we can create accurate, equivariant, and invariant models, even with linear fitting. And so this multi-ace is something that first, there will be a series of papers from this, but the first one is something that we are just waiting for the co-authors to read through the manuscript one last time before we put it up. So this paper, we actually set out all of the theory of how to go beyond a single layer ace and how this actually unifies basically all O3 equivariant intraatomic potentials that people have done before. So yes, finally, some big thank you to people. So Christoph Ordner is so a lot of the linear ace code that I've been working with is in this ace1.jl Julia package, and Christoph Ordner is leading the development of that. So for the reactive voter, Christoph Schahn is helping me a lot with expertise, and then Elias is doing all of the multi-ace work, and Gabor is supervising everything. So yes, thank you.